I'll start this. All right. I think we'll start with the outline for test 4. Let's see here. Whoop. Oh, wow. Let's screw that. 113. There. Okay. So, I'll just start by giving you guys the outline like I usually do for test 4, which is of course our last test, which you will be submitting to Gradescope. So that's why we had to have it all set up. So test number 4. You will submit to Gradescope so make sure it is up and running, right? Even if, because there are a surprising number of people who did not do the bonus assignment, which I don't know I didn't, but that's okay. And so make sure that you're up and running and you're able to get on there. People were having trouble, like I said, so make sure that you're able to sign on at least and able to upload stuff, and that you have a scanning app that you like, probably on your phone, that you know how to use and save a PDF. Okay, I think it even takes pictures or accepts pictures. I'm not sure. I would always just post it as a PDF, but who knows? So make sure you play around with that. The first question on test number 4 is going to be find the absolute maximum and minimum values on an interval. So find the absolute maximum and minimum values on an interval. And if you're not sure, you can look at the notes from March 24th. We've done it a lot since then, but that might be a good start. Okay. So because this test is open book, essentially, I don't really see the need to give you guys kind of practice problems because they would be way too similar. So we do want to keep it a little bit, I don't know, I don't want to say harder, but just a little bit more challenging, right? The questions are going to be reasonable, but I don't want to give you guys exact questions to work from like I did before. So I'll just point you to which day the notes are in, and then you can kind of go from there. And of course, you know, you're working at home, use your resources, don't work together because it's very easy to tell, especially if you mess up. But definitely use your resources, right? So if you know, don't be a hero here. I want you to use your notes. I want you to do practice problems beforehand, have those kind of worked out, that kind of thing, right? So I want this test to be really good. So the second question is going to be, given a function, given a function and its first and second derivatives. Now we haven't seen something like this, but we've always just found the first and second derivatives, right? So here it's saving you a little bit of time. So given a function and its first and second derivatives, Part A is going to be to find the intervals that it's increasing and decreasing on, or increasing or decreasing on. So find the intervals of increase / decrease. Part B, find the local max and min. Find local max and min. Part C, find the intervals of concavity. So find intervals of concavity. Oops, concavity, right? Up or down. And then part D, finally, even though you definitely use the critical points up here, so it's just kind of a gimme mark. How many critical points are there? How many critical points? And if you're looking through your notes, you can have a look at March 26th for this one, although we've used it all along here, right? And so all these tools we've seen since then, but that's where we introduced it. The third question asks you to use Rolle's theorem. Use Rolle's theorem. Oops. Rolle's theorem to show that the given function cannot have two or more roots. So it cannot, so essentially it can only have one root. It cannot have two or more roots, which is basically saying can only have one root, right? That was also on March 26th. So not a lot of notes to go through so far. So Rolle's theorem, remember, says that if you've got a beginning point and an end point and they're the same, then at some point, whether it goes like this or like this, right, we're going to reach a point where the derivative is 0. Fourth question, you're going to use L'Hopital's rule to evaluate two limits, right? You have to state the indeterminate form, but in general, use L'Hopital's rule to evaluate two limits. We did this last day on March 31st. And then the last question is an optimization problem, which we did last day, but I've got 2 more examples for us to go through, and then that'll be it for today. Optimization, and then it'll be just if you have any questions. Optimization problem, which is from March 31st, and of course, today. So 5 questions. That's the end of the test. Any questions? I'm going to check the chat in case because I know it's early, no one wants to put their their microphone on. None. No questions? All right. So like I said, we'll just go through 2 optimization problems. And that will be good. So here, 5 questions. When you're submitting to Gradescope, I'm gonna add another kind of an additional criteria, I guess, to the list that I gave you when you were submitting your bonus assignment. And so what I want you to do is use 1 page, right? Or use a new page for each question. Some of these will probably require more than 1 page, right? But if you put question 1 on a new page, it'll be easier to figure out where those questions are. So or where your work is, especially if you're not printing these off, then and you're just writing on paper on the side, that's fine. But just make sure that you use a new page for each question. I forgot to add that on there, but I think it'll be really helpful. Okay. So let's see here. So that was the test outline for next day. And like I said, use your resources. You're working at home. You've got all your notes. You've got access to the internet. I think it said something about don't use the internet, but honestly, how on earth am I supposed to know? So I think that's kind of a silly criteria, so I'm going to get rid of that. And just as long as you don't work together, because like I said, it'll be very obvious. So all right. So let's do, I've got 2 optimization, I've got 3, but I actually didn't like the 3rd one, so we're not going to bother with that one. So this is from exercise number 35 in the textbook. Okay. So it says that the top and the bottom margins, so the top and bottom margins of a poster are each 6 centimeters, 6 centimeters, and the side margins are each 4 centimeters, So we've got this poster, and one of the criteria or the constraints, right, that we were talking about last day is that the printed area in the center must be 384 centimeters squared. Find the dimensions of the poster with the smallest area. So find the dimensions of the poster with the smallest area. So these can be kind of tricky, right? Because you're given a word problem like this. We're not really used to word problems, or well, some related rates type questions, right? But word problems aren't that easy to deal with. but we start and we draw out the situation. So we've got this poster, and in the middle, we've got some printed area here, right? And what we're saying is that, okay, well, some of the criteria that we've been given is that the top and the bottom margins are 6 centimeters. So the top and the bottom margins, so from here to here, must be 6, and here to here is 6. We're also told that the side margins are each 4 centimeters, so from here to here is 4, here to here is also 4. So we've been given that. We're also told that this thing has to be 384 centimeters squared, right? So this area here is the printed area. It has to be 384 centimeters squared. So we know that we want to, well, we know 384 must be the length times the width, right? And we can figure out what the length times the width is, but we want to find the dimensions of the poster. So we want to find the dimensions of this outside thing, right? And so what we'll do is we'll just call this length, let's use a different color here. This length, let's call it X. And this length, let's call it Y. Yeah. So what that translates to, right? So if we're calling this length X and this length Y, what we're trying to find is X and Y, right? And so that's going to be the easier way to go about these is if you figure out what you need and call those just X and Y, or length times the width, or height times the width, or whatever you want to call them. It's easier if you're trying to solve for just those values, right? What you could have done, so what I'm trying to say that you shouldn't be doing is calling this X and saying that this is X plus 8. It works, but then you're solving for X plus 8 and Y plus 12, which is a little bit harder, right? So it's easier if you go for the longer distances, X and Y. But then by the same logic, right, we can say that this distance here, this distance, oops, from here to here must be X minus 8, right? Because it's a distance of X, but then we've chopped off 4 on each side. So X minus 8. Let me just clean this up a little bit here. Okay. There. And then same idea over here. This distance must be Y minus, oops, Y minus 12. And same idea, this is the length of Y minus 6 on each end, which makes 2 times 6, so Y minus 12 is the length there. Okay, so what we want to do, right, is find the dimensions of the poster with the smallest area, right? So if we want to have the smallest area, so the smallest X times Y, well, then we're trying to minimize something. And so the area to be minimized, well, area is the length times the width, right? Or in this case, the area is Y times X. So the area is YX, right? Or XY if you prefer. Okay. So we're trying to minimize y times x or x times, I actually prefer to write x times y. It just sounds better, xy. So let's do that. All right, it doesn't matter. But the constraint that we've been given is that the printed area has to be 384, which means that x minus 8 times y minus 12 must be 384, right? And so the constraint is that the printed area must be 384 centimeters squared. Yeah. Which means that y minus 12, or I'll start with the x's because it just sounds better. X minus 8, and it's what I have in my notes, otherwise I'll get confused. X minus 8 times y minus 12 must be 384. I'm ditching units just to make it easier. From the context, we'll know that the area must be centimeters squared, right? The lengths must be in centimeters then. Here, remember what we do is, okay, well, if we want to minimize the area, which is x times y, I can only have the area in terms of one of these variables. So in here, I either solve for x or I solve for y. Either way, it doesn't make a difference. I'm going to solve for y and then use that y in my area function. So here, I'm going to solve for y or x and substitute it into a. A equals x times y. So here I've got x minus 8 times y minus 12 must be 384, which means y minus 12 must be 384 over x minus 8. So y must be 384 over x minus 8 plus 12. So now I can substitute that into, therefore, a of x must be x times y, but that's going to be x times y over the page break. I'm not sure how good that's going to look later, but whatever. X times 384 over x minus 8 plus 12. So now this is how I'm going to get the area just as a function of x, right? So now I've got this area function. I can expand this x in here, make it a little bit nicer to look at. Not a lot like nicer, but a little bit nicer. So I get 384x over x minus 8 plus 12x. I've got this area function now. I want to minimize this thing, right? Remember, you want to minimize it. Either way, if you want to maximize it or minimize it, you're going to do the same thing, right? You're going to find the critical numbers and see where it's increasing and decreasing. Okay, so here, we're going to find the critical numbers. And then use the first or second derivative test or the closed interval method to find the minimum. Then use the first or second derivative test or the closed interval method. I always prefer the closed interval method if I have one, right? And so if I have a closed interval, then I think that's the easiest thing to do, right? Is to figure out where your critical numbers are evaluate the function at those critical numbers, evaluate it at the endpoints, and then you'll know which your max and min are. But if we don't have a closed interval method, or the closed interval method to find the minimum. Oops. To find the min, boy, just changing everything I write here. Minimum. Okay. One thing that we'll keep in mind, right, is that x has to be more than 8, right? Because I have to subtract 8. So x has to be greater than 8, but also y must be greater than 12. But because we wrote our area in terms of x, really the only thing we need to keep an eye out for is x, and then the y will be taken care of in there. So we must have x greater than 8. Okay. Should be nice crisp greater than. So we must have x greater than 8. Otherwise, x minus 8 will be negative. In fact, it can't even be equal to 8 because then x minus 8 would be 0, and then the area would be the height times 0, which would be 0, so not 384. So that's why it can't even be 8. So what we're going to do, keeping in mind this constraint on x, I don't have a closed interval, right? And so what I'm going to do is I'm going to use I don't know, first derivative test is probably my go-to after the closed interval method. So for me, my preference is the closed interval method if I can, then the first derivative test, fine. And then the second derivative test is a little bit sketchy, so I would use that if the first derivative test doesn't work. So let's see here. We have to find the derivative of this thing, right? And so we've got a of x, just writing it out so I have it here, is 384x over x minus 8 plus 12x. Okay. So the derivative of a with respect to x, here we've got this quotient rule, right? So we've got g is x minus 8 times the derivative of f, which is 384, minus f 384x times the derivative of g, which is 1, over x minus 8 squared, right, over g squared. And then here we're just adding, we can kind of think of this as a polynomial, right? We go through, find the derivative of this, and then because we're just adding the derivative of 12x is 12. So we'll do a little bit of work to simplify this thing, right? We can make this look a little bit nicer. And so if I expand that x minus 8 out, I get 384x minus, and then 384 times negative or times 8 is 3072 minus 384x over x minus 8 squared, and then plus 12. Don't forget that plus 12. 384x minus 384x goes away. Remembering that you've got this negative here, also don't forget about that. Negative 3072 over x minus 8 squared plus 12. Okay. This is my derivative. I don't see any way that I could simplify this anymore. Um, so this thing, right, is going to help me find my critical numbers, right? And so here, first thing is we're going to find the critical numbers. Type 1 is when a prime of x equals 0, and type 2 critical numbers is when a prime of x does not exist, right? Which is obvious here when x equals 8, right? I've got this, the derivative doesn't exist because I'm dividing by 0, right? And so let's start with our type 1. We want negative 3072 over x minus 8 squared plus 12. We want that to equal 0, not 8. There. To equal 0. So just to kind of ditch this negative here, and it doesn't matter which order you do it, but I'm going to move this this negative value over to the right-hand side. So then I get, but then I'll probably revolving door it, so I get 3072 over x minus 8 squared is 12. Right. Kind of pulling a fast one here. Not really. You're welcome to just do stuff like that too, right? At this point, I expect you to be pretty comfortable, actually really comfortable moving things around like that. So 3072 is 12, oops, is 12 times x minus 8 squared. If I divide both sides by 12, I get 256 must be x minus 8 squared. If I take the square root of both sides, then I get the square root of 256 must be x minus 8. Oops. X minus 8. But if I take the square root, it's the plus minus square root, right? And so, because if I take it back, right, and I square it, then both the positive and the negative would work and give me 256, right? And so what we have to consider here is, okay, well, if we have negative root 256 equal to x minus 8, then we get, well, the root of 256 is 16, I think. 256, oops. Square root of 256 is 16. So then we get negative 16 is x minus 8, which puts me at x must be negative 8. That can't be, right? Can't be in this, or can't have x equals to negative 8 in this situation, right? In other situations, maybe, but we can't have a negative length, and so that option is out. So now I'm going to focus on the positive root of 256 equals x minus 8, which is 16, which is x minus 8. So x must be 16 plus 8, which is 24. Okay. So here, this, we only have one type 1 critical number. So here, maybe I'll use a different color. This is our type 1 critical number. The type 2 critical number is quite a bit easier, right? That's where the derivative does not exist. In this case, we can easily see that that's when x is 8. So the type 2 critical number is at x equals 8. so if we've got these two critical numbers, right, we've got our type 1 at x equals 24, our type 2 at x equals 8. It doesn't matter which type it is. They're both critical numbers. It's just, I'm just highlighting how we found them, right? How we found them is two different methods, type 1 and type 2. So if I use the first derivative test, that's where I draw a number line here, and I know, well, actually, we decided that x had to be greater than 8, right? And so how about we put 8 there, but also because it's a critical number, it had to go on our number line, but also we decided that it had to be greater than 8. And then I'll put 24 on here, and then things just keep going and going and going. So the first derivative test says that we need to find the sign of the first derivative in each of these intervals, right? And so between 8 and 24, it'll all behave the same. And so I'm just going to pick a value in here just as a reference point. What's going to be easy? Maybe if I do something like 10, just in my mind, right? And then maybe something like 30, because I just want to figure out if I get a positive or negative. So the derivative a prime of x is negative 3072 over x minus 8 squared plus 12, right? So here I get a negative number over, and then 10 minus 8 is a positive number squared, which is still going to be positive regardless, right? But it's going to be positive plus 12. I guess we're better off. So negative 3072 over 10, just to make sure, is, well, it's going to be positive, or sorry, it's going to be negative, because the negative 3072. But let's just do it. So 10 minus 8 is 2, of course, and then square that. Negative 3072 divided by 4 plus 12 is a very negative number, negative 756. Whereas here, we've got negative 3072 over, let's do 30, right? Just any number in that interval will do. I'm just picking a random one. And let's see if it's positive or negative. So negative, so 30 minus 8 is 22. Square that. And then negative 3072 divided by that guy plus 12 puts me on a positive number. Right. So what that tells me is in this interval, right, we've got a decrease, and then in the 24 and greater, we've got this increase, right? And so here we've got this decrease going to an increase, making this a local minimum. Maybe I'll use a different color there. But which? There. So 24, x equals 24 is the minimum, right? And so here we find the minimum value when x is 24. Okay. And so, well, we wanted to find the dimensions of this thing and probably the area too, just to make sure. So now we can find y from before, right? We made that substitution because y, where here. Y is 384 over x minus 8 plus 12. Let me just copy this so I don't have to remember it. Copy. Paste. Move that over. It's like nothing ever happened here. There. Find y, which is 384 over x minus 8 plus 12. So y must be 384 over 24 minus 8 all plus 12. So y must be 36. Therefore, the dimensions that minimize, that minimize the area, the total poster area are 24 centimeters wide and 36 centimeters tall. Right. And the total area would be 24 times 36, so 864 centimeters squared. Right. It didn't ask for that total area, but sometimes it's just nice to wrap it up. Okay. I'm going to check for questions about that one. I haven't seen any, but any questions about that one? No. So, like I said, I only have two examples prepared, but as you'll see, right, they take a little bit of time, and so I've just got this next one, and it has to do with volume. And here's my hint for the test is that it will be a volume type question. So, but you know the volume function, it's just the length times the width times the height, right? So we've been dealing with areas mostly, or distances and that kind of thing, right? And so just be prepared for a volume question. Too far. Okay, so here, that's the end of that question. So this is exercise number 16 in the textbook. And there's a lot more exercises, of course, that you can do to practice, especially now that I've told you it's going to be a volume one. You could try to figure out all the volume ones at least. Okay, so here's the question. So a rectangular storage container with an open top is to have a volume of 10 meters cubed. So here we're told what the volume should be. Another option would be, okay, we have some other constraints and we want to maximize or minimize the volume. So there's a lot of different things that we could do here, right? But as long as you've seen one where you use the volume, I think that'll be good. So the length of its base is twice the width. So the length of its base is twice the width. And material for the base costs $10 per square meter. So material for the base costs $10 per square meter. whereas the material for the sides costs $6 per square meter. Find the cost of the materials for the cheapest such container, right? So find the cost of the materials, find the cost of the materials for the cheapest such container. Cheapest such container. Okay. So I'll put the rest on the new page here. So we've got this this container, and if we just draw a box, it doesn't have a lid. So I'll just draw this kind of, I'm not very good at spatial drawings, but it doesn't really matter. See, it always looks a little lopsided here. I feel like I need to extend it a little bit. Now it's lopsided the other way. Oh well, whatever. So here is my rectangular storage container, right? So I've got a rectangular storage container with an open top, and it has to have a volume of 10 meters cubed. The length of its base is twice the width, right? And so here, if we start out and we say, this is the length and this is the width and this is the height, right? Well, the length, what we're told, is that it must be 2 times the width, right? So we can make that replacement right away. So the length of its base is twice the width. Okay. Material for the base costs $10 per square meter, right? So here we've got this completely lopsided, but that's okay. Right, and so here, the materials for this base here is $10 per square meters, right? And so what we're saying is that the cost is going to be 2W times W at $10 per square meter. Okay, so we'll incorporate that later, but then each of the sides only costs $6 per square meter, but there's 4 sides, right? And so we want to minimize this cost, which is a little bit different from what we've been doing, but not much. Right, and so we know that the volume of this thing must be the length times the width times the height. Okay. We're told that the volume has to be 10, right? And so here, this is a constraint, is that the volume must be 10, but also that the length, we can replace it with 2W times WH. So 10 must be 2W squared H. What I'm going to do is, because it's going to be easier to solve for H, right? If I solve for W, I have to take the square root, and you definitely could do that. I wouldn't recommend it, right? And so I'm just going to solve for H here. But like I said, you can solve for W. It's just going to be way harder. So what we find is that H must be 10 divided by 2W squared. So H must be 5 over W squared. Okay. We wanted to minimize the cost, right? So here, I'll just make a note here. Minimize the cost. Okay. So we need a cost function. Need a cost function. Okay. All right. So if we need a cost function, well, then we need to figure out, well, what is the cost of this thing? So if we've got one of these at $10 per meter squared, 4 of these, right, but they're going to be different dimensions, h times 2w, there's two of those, right? The front and the back, let's call them. And then there's h times w, there's two of those for the two sides, right? And so what we've got is, let's talk about the base, all about that base. The base is 2w times w, which is 2w squared, and the cost for the base is $10 per meter squared. Let's talk about the sides. The sides, well, there's two sides that are going to be 2w times h, right? And then there's two sides that are going to be just w times h, right? Just thinking about what these, so wh, because this is also h, right? So wh, there's two of those sides at $6 per square meter, and then h times 2w, there's two of those. And so, and the cost is 60, whoa, yikes, $6 per meter squared. Okay. We can expand this and kind of simplify. So what we do is we get the sides must be 4wh plus 2wh. So we must get 6wh. Right? And then I'll move this cost down at a cost of $6 per meter squared. And then I can move that up there a little bit cleaner. In fact, to match what I did earlier, right? So now we've got 2w squared at a cost of $10 per meter squared, 6wh at a cost of $6 per meter squared. Remember that h, we already solved for h. Whee! Right, and so that's where we're going to use it. Here, right, we, like I said, we could have just as well solved for w and replaced w here. But because this is in terms of w, it's cleaner, but also I don't want to be dealing with the square root, right? The plus minus, it just, no thanks. So the sides must be 6w times h, which is 5 over w squared, which is going to be 6w times 5. So I get 30, let's see here, yeah, 30, 30 over w. Okay. Let me see here. I did something else. And now 6 times. Okay, it should still, yeah, that should work. Well, yeah, it should work. So I just did something else in my notes, but it'll come together. So now I've got both of these in terms of w. I know the cost. So what I can do is I can develop the cost function. The cost is one base, right, at $10 per meter squared. So at $10, I need 2w squared. And then at $6, I'm going to need the sides, which I've already kind of computed, and worked out to be 30 over W. 6 times 30 over W. Oops. Okay. Good. So the cost is a function of W, right? There's the only variable, or W is the only variable in here. And if I just ditch the units for a little bit, because it's obvious that cost should be in dollars, right? Or whatever, whatever currency you're working in, of course, but 20W squared plus 6 times 30, which is 180 over W. Okay. Oy. Turn my W into some sort of weird, there. Okay, so this is my cost function, right? And we want to minimize, this, right? And so we can use, I don't have a closed interval, right? Otherwise that would be my go-to. But to minimize this, I can use the first derivative test, so I can find my critical numbers, and then I can check when the first derivative is negative or positive and try to find that minimum, just like we did for the previous question. And so we need to find, oops, find critical numbers. Which means I need to find the derivative. The first derivative of this thing is going to be 40W minus 180 times W to the negative 2, which is over W squared. Okay. If I want to deal with this thing, I think it'll be easier if I put it over a common denominator, right? And so here, because I could solve for where this thing is 0 and where it doesn't exist, but I think it'll just be easier if I just put it over a common denominator. And so we've got 40W times W squared over W squared, so times 1, minus 180 over W squared. So I get 40W to the 3 minus 180 all over W squared. Got that common denominator. So now I want to be able to show where this thing equals 0. We can factor out a common 40, even though it's not obvious, right? But what we'll do is we'll save ourselves a little bit of work. I guess it doesn't really matter. No, how about we leave it actually? And then, yeah, might be cleaner. And so we've got a type 1 critical number when the derivative is 0, right? That's going to be true. So here's our derivative, right? That's going to be true when 40W to the 3 minus 180 is 0. So that's when 40W to the 3 minus 180 equals 0. So I get 40W to the 3 is 180. W to the 3 is 180 over 4t. And so 180 divided by 40 is 9 over 2. Or you can leave it. Might be nice to have a calculator that just simplifies that for you. 9 over 2. Like mine does. So I get W is the plus minus, oh, not plus minus, because it's the third root actually. So we don't need it, right? The third root preserves the negative. So we get the third root of 9 over 2. This is our type 1 critical number. Type 1 critical number. Our type 2 critical number isn't going to be that interesting. That's when W is 0. We're not interested in W equals 0 anyways. And so because that would make the width 0, it just is not that interesting. So the type 2 critical number is when W squared equals 0, right? So when W equals 0, right, but not interesting. I shouldn't say that. Oops, just kind of all over the place here. Not a possible width in this situation, right? So we'll start there, but the width isn't going to be 0, so it's not really going to be a point that we're interested in. So what we do, right, we can use the first derivative test. And we can say, okay, well, I've got this number line here. Let's start it at a W of 0. And then my second critical number is the third root of 9 over 2. And just so you know what the third root of 9 over 2 is, to the power of 1 over 3. That is roughly 1.65. So just so we know kind of what this thing looks like. Oops. And then it keeps going and going and going. So when I pick my critical numbers or my test points, right, I'm going to pick maybe 1 and maybe 2, right, on either side of 1.65, but on the positive end. So I'm going to use my first derivative to test this thing. So my first derivative, right, was 40W to the 3 minus 180 over W squared. So 40W to the 3 minus 180 over W squared. If I use a width of 1, I get 40 times 1 to the 3 minus 180 over 1 squared, which is going to be negative. In fact, I'll replace these ones with pink values because they could actually be any of those values. Same idea here, right? I get, let's scoot it down so it's on the same level. First derivative is going to be 40 times 2 to the power of 3. I'll replace it with pink later. Minus 180 over 2 squared. 2 and 2. How about that? So when I go ahead and do this, I get a positive number, 2 to the power of 3 times 40. It's 320 minus 180, so it gives me a positive over a positive. So I get a positive value. Oi, square around it. It's ultra sensitive today. So what does that mean? That means that the cost function is decreasing here and increasing here. Okay. Making this a local minimum at W equal to the third root of 9 over 2. So the cost, therefore, the cost is minimized when W is the third root, of 9 over 2, which means that the cost of W, the cost function, remember, is that original, where was it here? the cost function, I'm just going to steal it here. Whee! Copy. Let's erase this. Paste. So what we have is the cost at the third root of 9 over 2 is 20 times the third root of 9 over 2 squared plus 180 over the third root of 9 over 2. A little bit nasty, but what we get is that the cost is approximately, because I've got it on the side here, 163.54, and it's a cost, so it's in dollars. Therefore, the minimum cost of the box is $163.54. Nice. All right. So that one, so both of these are quite long, right? But that's because I'm kind of talking you through it. There should be a kind of a pattern for these optimization problems, right? And so what you do is first you sketch out the problem, right? You kind of read through it, sketch it out, sketch it out, try to figure out what things look like, identify your constraints, right? Because that's going to be how you swap out one of the variables, and then write your function that you're trying to maximize or minimize. Then you're going to find your critical numbers, and then probably use the first derivative test. In fact, yes, use your first derivative test to figure out where this function is increasing or decreasing, and then evaluate the original function, right, to figure out what the max or the min is. Any questions? Let's see here. Hey guys. I see no questions. So like I said, those are all the examples that I have for us today, or at least that are helpful, because I've got another one, but it's actually not that good, so I'm not gonna do it because it won't help you for the test. So like I said, for the test, you've got a volume optimization problem. All right. I still see no questions. Well, okay. Well, that's all I've got for you then. So you've got your test 4 on Tuesday. It's going to be in the regular class time. What I'll do, because I know, well, you see, not everyone is here, so I'll send out an email with specific instructions for test 4 on Tuesday, but it'll be in our regular class time, and you're going to upload it to Gradescope. So, but it looks, I think everyone got that all figured out. That's here at least. But if you didn't, let me know. All right. I still see no questions. So then I will say goodbye. Okay, see you later.